Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, I will go over another method in engineering where we calculate deformation, but I'm not going to use it to calculate deformations. Oh, yeah, this guy is crazy, right? Okay, basically, it's called the slope deflection method. So since we already have other easier ways of finding deflections, like we did the conjugate beam method and we did the Castigliano's theorem, and I think it is better to use it in a more important thing. And what is that? Continuous beams. When you have indeterminate beams or indeterminate frames, you probably can use another method to find the deflections and the slopes, but the slope deflection method can help you in a much easier way to find the reactions, the missing reactions at the support. And maybe without discussing, the derivation or anything, I'm going to show you what we are going to do. So first of all, we have the slope deflection method. And the slope deflection methods is done on two steps. So the first step, for every part of the, or for every base, so to speak, in your continuous beam, we are going to go to the internal supports and fix them. And we calculate something called the fixed end moments of any part. So to give you an example, in fact, let's draw an example and we show you what we are going to do, and then we apply that and do it, right? Let's say we have a continuous beam. So well, it doesn't matter. I'm not going to draw it to scale. And let's say it's fixed on both ends. Oh my God. So that's already 3 unknowns. And then in the middle here, I have another support, a roller. And let's say that this beam is loaded as follows. I have a distributed load on the left side. And a different distributed load on the right side. So maybe the left is larger. Doesn't matter, you can do either way. Let's say this thing is 20 kilonewton. Maybe you can do it higher, but it doesn't matter. It's the method, not the actual values. 20 kilonewton per meter, and this is 10 kilonewton per meter. And let's say that each bay here is, what, 3? You get 4 meters long. We know, or you should be able to find in a table, the fixed end moment of a beam that is loaded with a distributed load, right? So basically, I have a beam, which is AB, and BC is the same thing. The only difference is the magnitude of the distributed loads. This thing has a distributed load like that, W, and this is L. So the end moments are WL square over 12. In the slope deflection method, the end moments are considered positive if they are clockwise, and negative if they are counterclockwise. That's opposite to what we did when we were starting solving moments in statics, right? We used to say, well, and then when we analyze the beam, of course, counterclockwise would be positive. So the only thing is that we are going to work out until we find the moments. Notice that after that, we are going to look inside the beam to find the reactions at the supports, in which case I'm going to switch the sign of the moments. Because if I get a negative moment meaning it's going clockwise like that, and this one will be counter it, so that would be positive because it's going clockwise, and that's negative. Okay? But then if I end up with a clockwise moment here, it would be negative when we analyze the beam, and this would be positive, right? So you have to be careful with that. Okay, having said that, so the first part, step number 1, I'm going to find the fixed end moments at each thing. But then before doing that, I'm going to break AB into that, and BC also into a fixed support. That's why we call it the fixed end moment. Okay, let's do the math as we go, and then we see what we do after that. So I'm going to say fixed end moment AB equals negative, the W is 20, L squared is 16 over 12. I can simplify this as 4 and a 3. So I get negative 80 over 3 kilonewton meter. I don't need to calculate FBA because it's the same thing. The moment here is the same thing, right? Except that it would be positive. So FEM DA, meaning the moment at B in the direction of A, meaning I'm looking at this portion of the beam, would be 80 over 3 kilonewton meter. I'm going to repeat that here. Find the moment BC, which definitely would be half of that because it's the same length, but half the load, right? So fixed end moment, that should be the easiest part, whether it's a concentrated load in the middle or at a distance of A and B, or, you know, 2 concentrated loads or triangular load. All of these, you can find them easily in any table. So this guy would be negative 40 thirds, so we don't waste time, right? And the fixed end moment CB would be 40 thirds kilonewton meter. So that's the first part, and it's so easy. The second part, we apply the equation of the slope deflection. And what does this slope deflection equation say? It says that the bending moment at say AB equals the following: 2EI over L times, so always 2EI over L outside, okay, times twice the slope of the close by support plus the slope of the far end support. So when I go here, it would be 2 theta B plus theta A, okay? Minus 3 times psi. What is this thing? This basically is delta, which is the deflection over the length. So deflection per unit length. Notice both of them are meter or millimeter or centimeter, it doesn't matter, but distances. So epsilon is dimensionless, like theta and theta, right? These are in radians, so they are not also, they are dimensionless. So we know that, so at the end of the day, also we call I over L, we call it the stiffness K. So to just simplify the writing. So in this case, and then you add to that the fixed end moment, which is negative 80 over 3. Now, A is a fixed support. Now we are talking about the whole beam, not this part, okay? This is fixed, so 0 rotation. A and B are supports, so there would be no deflection, unless the problem tells you, for example, point B has a settlement, say, of 3 millimeters or something, in which case this rotation, because it's clockwise, it would be positive also, like the fixed end moment. Anything rotating clockwise would be considered positive, counterclockwise would be considered negative. In this case, of course, it's a regular beam. There is no settlement that occurred, so that guy would be 0. So really, our equation is so easy now. Let's write the equation for MBA. No, we are not going to study for an MBA. Okay. MBA would be 2E, I'm going to call it K now, times theta sub A, which is 0, plus twice theta sub B, because I am at point B, so it's twice, minus 3 psi, which is 0, plus 80 thirds. See how easy it is? Okay, now let's write MBC. And that's a channel in the Middle East. So anyway, yeah, because I said MBA, so I have to say something for MBC. 2EK times twice theta B plus theta C, but C is also a fixed support, so theta C is 0. There is no rotation. Minus 3 psi, which is 0, minus 40 thirds. And finally, MCB is twice EK, twice theta C, which is 0, plus theta B, minus 3 psi, which is 0, plus 40 thirds. And you say, okay, so we are stuck. We don't, of course, E is given to you, I is given to you, and we don't need them because we are not calculating deflections or so I didn't make up numbers for that, right? We are simply want to find, we want to have the moments, we will find them, and then I need the reactions at the support, A, B, and C. In fact, B, who can think about it and tell me what they expect the vertical reaction at B to be? At B to B, yes. Common sense would say, if this is distributed, I will get half of that here and half of that there, but then the moment will change this. This will give you half of that here and half of that there, but the moment at C will change YC. But YB should be half the total load. It's taking half of the left and half of the right. So 20 times 2, not 4, is 40, and 10 times 2 is 20, 40 plus 20. I should expect By to be 60 kilonewton up. Everything is symmetric. We'll see. Alrighty, so after doing that, I'm stuck. I have E and K and theta, and I have something very important. I know that the total moment at B equals 0. What? Yes, because this moment that we consider to be positive on the left is exactly equal to another moment that is negative on the right. You see negative 40 at B. No, I'm not talking about these moments. I'm talking about if you draw BC, that positive moment, I'm sorry, that's negative moment and that's positive. Why did I say, yeah, that's positive and that's negative, right? Because you said clockwise is positive in this method. So these two are equal to each other. That's why you say that, but they are opposite in sign. So I can say now that MBA plus MBC always equals 0. One of them would be positive, the other is negative, but they have to be the same, right? Cannot be, or else the beam will turn. Okay, so let's do that math. If I add these two lines together, MBA plus MBC, notice I have 2EK, 2 theta, 2EK, 2 theta. So this is like 4EK theta B and 4. So they add up to 8EK theta B. Plus 80 over 3 minus 40 over 3 would be plus 40 thirds equals 0. Say, would that help? Yeah, wait a second. We are solving for theta B. And you can see I can simplify the 8 and the 40 and make that 5. So when I move it to the left-hand side, it would be theta B equals negative 5 over 3EK. And then I'm going to take that, plug it in each one of those. Really, it's not hard once you get the gist of it. Now we are going to say, what is MAB? It's 2EK, 2EK times theta B. Oh, but theta B is negative 5 over EK minus 80 thirds. The EK and the EK cancel. Negative 10, right? Is it? Theta. So I didn't divide by 3. So, okay. So theta B is negative 5 over 3 EK. And then I have 2K theta B. Okay. So these cancel. You get 2 times negative 5 is negative 10 thirds and negative 80 thirds. So it's negative 90 thirds or negative 30 kilonewton meter. Okay. Now we go to MBA. 2EK times 2 theta B. So it's 4EK times negative 5 over 3EK plus 80 thirds. 4, these cancel. 4 times negative 5 is negative 20, plus 80 is 60, divided by 3 is 20 kilonewton meter. Now, MBC. If we don't get negative 20, something is wrong. We did a math error, right? We said here they are add up to 0, meaning they are equal and opposite. Excuse me. So MBC, 2 times 2 is 4 EK times negative 5 over 3 EK minus 40 thirds. 4 times negative 5 is negative 20, minus 40 is negative 60, divided by 3 is negative 20 kilonewton meter. Nice. We check this out. Finally, we get the MCB. It's just 2 EK, so 2 EK times negative 5 over 3 EK, which is negative 10 over 3, plus 40 over 3 is 30 over 3, or 10 kilonewton meter. And I found all the moments. Okay. I still don't know the vertical reactions. So what do I do? Now I'm going to take this beam, or this part of the beam. Notice I know the moment at B. The moment at B is the 20 kilonewton meter. So if I take this portion and calculate the moment at B, knowing its magnitude, I can solve for AY. That's, of course, I have a moment here, a moment there, distributed load, and a reaction. So let's, do I have, oh, I'll get a piece of paper to continue the problem. So now I will have my beam, AY, BY, which I said I assume it's 60, and CY, just because this problem is distributed symmetrically. But okay. I have here the 20 kilonewton per meter, and here the 10 kilonewton per meter, and 4 and 4. And the moments, of course. So we have the, yeah, I need to say something here. Okay. So notice we have a moment of negative 30, meaning it's counterclockwise, because we assume that if it's counterclockwise, it would be negative, and we ended up with MAB being negative. But in the analysis, it would be positive, right? Because it's rotating counterclockwise. So I'm going to say, for example, we can do summation. We'll get the summation of the moment about B just from the left hand side. Why? Because I already know the moment here. So there is no reason to take for the whole, I cannot even take the moment for the whole beam because I have 3 unknowns, unless I say this is 60. So what we say, which is completely legal, is to say, no, I'm going to take the moment only of this piece. I have a 30 here, and I have a positive 20, so it's going clockwise here. I have AY, and I have the distributed load. So I can find AY by taking the moment about point B. Do you see that? Hopefully, yes, right? So I'm going to write my equation. This moment counterclockwise is positive. That's why I will change the sign. I will say this, instead of being negative 30, I'm going to say 30. The AY is rotating clockwise, so minus 4 AY, since we said this is 4 meter and this is 4 meter. Plus 20 times 4. The center of mass is in the middle at a distance of 2, so times 2, minus 20, which is the positive moment here at BA, equals 0. So I get, when I move the 4AY to the other side, it would be 30 plus 160. That's 190 minus 20 equals 170 kilonewton. Then I'm going to divide both sides by 4. 16 over 4 is 4, and 10 over 4 is 2.5. So I get 42.5 kilonewton going up. I can take the summation of the moment about B, but this time from the right, right? So again, here it is, 10 kilonewton per meter. This is 4 meter. This is CY. This is point B. And the moments. The moment here is negative, meaning it's going clockwise. So I will consider it positive. This one is positive 10. Oh, I'm sorry. I'm sorry. I think I mixed it up. This is going counterclockwise because it's negative. So I would make it here positive. Negative? What am I doing? Yeah, it's negative, meaning it's going counterclockwise. So in our analysis, it would be positive. And this guy, the 10 kilonewton meter, is positive, meaning it's going clockwise, so we will consider it negative here. So when I write the equation, I'm going to say, I'm taking the moment here. So I'm going to say 4cy minus 10 plus 20 minus 4 times 10 times 2 equals 0, because this load is rotating clockwise. 20 minus 10 is 10, but this is 80, right? So when I move them to the other side, it would be 80 minus 10, or 70. 4cy is 70. I'm going to divide by 4 both sides. So that becomes 17.5 kilonewton, positive, meaning going up. And finally, I can say sum of the forces in the y equals 0. I have AY 42.5 minus 20 times 4 minus, plus BY minus 4 times 10 plus CY equals 0. 17.5 and 42.5 is 60. 60 minus 80 is negative 20, minus 40 is negative 60. Move it to the other side, you get BY equals 60 kilonewton positive, meaning going up. So we found everything. We started with 2 fixed ends and a roller in the middle, and we were able to find the moments at the ends at this load, as well as the reactions at the supports. Now, the last step, usually, why did I find all that and stop here? No, I will have to draw the shear force and the bending moment diagrams. So let's do that. Let's draw the shear force diagram. If I say, for example, this is 4, so from 5 to 1, and 3 is the middle. Shear force diagram. I start at A by going up to AY, right? And AY was 42.5. So I will go up and assume this is 42.5, something like that. And then I'm going down to constant, meaning that would be, when you integrate, it would be linear, 20 times 4 or 80. Meaning I will go down at B to 80, meaning 37.5. So it's roughly the same distance. Of course, I'm not going to draw to scale. I'm going to get shorter, a little shorter. Notice not to scale. We are just going to write the values. So this is 37.5. Then I will go 60. Remember, we said we are going to go 60 up, meaning 22.5, which is roughly half of that. Not exactly, but roughly. So maybe here, we said 60, so 22.5. And then we are going to go down 40, 4 times 10, meaning to negative 17.5. So again, maybe half of that, roughly. Oops. Something like that. No, shorter, maybe till here. Again, as I said, it's not to scale, so it doesn't really matter. To 17.5. Remember, the reaction at C was 17.5. And that would bring me to 0, so we didn't do any math error here. But how should I draw the bending moment diagram? Again, I don't like to integrate and have a function and, you know, substitute. No. I will find the distance where it crosses the 0. And you say, oh my God, that's too much work. No, it's not. You know what is this distance? They add up to 4. But the ratio of this to that, because these two triangles are similar, is the same as the ratio of this to that. So basically, you see how easy I'm going to do it with a calculator. I'm going to say, oh my God, what is that? Log, okay. 42.5 divided by the sum of 42.5, and which is 80. Remember, we had 20 kilonewton per meter times 4 is 80. So divided by 80 times 4. It's 2.125. And then 4 minus that will give me 1.875 is this part. That's how simple it is. It's much easier than to have a function, integrate it, and do this and do that. It's so much easier to do it this way. Again, 22.5 divided by 40. So this would be 2.25. Do you see it? Because you're going to say divided by the sum of the two, which is 4 times 10, which is 40, and then you multiply by 4. So you'll get 2.25. And this one, of course, would be 175 meters. 4 minus that is that. So we are done. What do you mean we are done? Yes. Don't you know that the moment, bending moment, is the integral of the shear force diagram? And that integration is the area under the curve. So I had the moment at A was negative 30. Negative 30, right? So I will go down a distance of 30. Let's say I'm going to use each inch here or something is 10. Or should we make it 1.5 so it won't be too, yeah. Negative 30 kilonewton meter. Oh, but I'm going to go up a distance equivalent to the area of that, which is, so I'm going to say negative 30, but then I'm going to add this area, which is 1/2 base 2.125 times height, which is 42.5. I will get to 15, 16. So at that distance, this distance is drawn, it's not drawn properly, but if you have to go to 15, and we said this is 10, it goes somewhere here, and this is 15.15625 kilonewton meter. But this is linear, so that would be going quadratic, right? It goes something like that. It reached the maximum here at the 0 shear, and then it will start to go down. But how much will it go down? Notice I already have this moment here, so I'm going to subtract from it the area of that triangle. 1/2 times the base, 1.875, times the height, which is 37.5. I will go down to negative 20. So at point B, I will be at negative 20. If that's negative 30, negative 20 is here. Again, you try to draw it, not. So this will start going, that's a minimum, local minimum. And then at, oh my God, at 2.25, which is further to the right, you know, that should be longer than that by half a meter, I will go up again, but I will go up like that, right? The slope here was high, it gets slower and smaller and smaller. All righty, so I have this value as negative 20, and I'm going to add to it 1/2 times 2.25 times 10 times that, times 22.5. And that will take me to 5.31. So somewhere here, I will go to 5.31, somewhere here or something. Then I'm going to subtract this. Subtract 1/2 times base 175. Of course, the height is 10 times. So times 17.5. Excellent. I ended up with at negative 10. Exactly at negative 10 because I know the moment at C was 10. So I will go down to negative 10 and then up to 0. So I started at 0. I ended at 0. Well, I ended at 10, but when you add the external moment, which is 10, and this was 5.3125. And that's it. Negative moment here, positive moment here, negative moment here, positive moment here, and a small negative moment here. What do you think? Well, it took us long because I was explaining and showing you what we need to do, writing the equations, but nothing was hard, right? I hope that's the case. If not, please let me know by dropping me a line in the comment section, and I will get back to you as soon as I can. Otherwise, hope to see you soon. Have a great day.